This is a broken SBL1. This is what it looks like when I remove the silicone rubber. I have removed the diode ring and connected the transformers back to back. Here is what I see from 300 kHz to 1.3 GHz. At 500 MHz, the attenuation is 6 decibels. So part of the loss of this mixer is from the ferrites, at least at higher frequencies. Well, my interest is 10 MHz at the moment. So from 300 kHz to 15 MHz, this is what I see, and the loss at 10 MHz is 1.7 dB. And that seems very reasonable. I will now look at this transformer back-to-back combination with strong signals to see if I can see noise produced by it. Between the signal source, the local oscillator, and this coupler, and the low-pass filter and the coupler to the spectrum analyzer, I have inserted the notch at 9.95 and a stepped attenuator and this back-to-back arrangement of transformers from the SBL1. And with different settings on the stepped attenuator, I have measured the carrier on the spectrum analyzer, knowing the coupling and error of the analyzer. Then this column is the calibration I had to put into the Linrad S-meter graph to have the reference signal, which is 50 decibels below, at the right level. And then the S-meter reading and the correlation reading. From that I can compute dBc per hertz and also noise in dBm per hertz. And then the noise increment means how much the noise increases above the limit at very high attenuation. And from that, knowing the limit, I can compute the noise of the sideband noise added, and in dBc per hertz, and it turns out to be fairly constant. It is minus, well, it's the noise is stronger at high signal levels, 182, 183, and it approaches 184, 185, 186 perhaps, at power levels of maybe 12 dBm or so. The compression here comes from the carrier level and the S-meter calibration number. And this looks, I have some compression in the Schottky diodes, probably. We will see later on that this is not right. I have removed the back-to-back transformer as for a reference and measuring what happens in this situation. The noise, dBc per hertz, is much better, and as expected, it doesn't change when the attenuator setting is changed, not until the attenuation is very large, because then there is accuracy problems. But the compression I compute is 3 decibels almost, and I have a problem understanding this. So I added a cable 3/4 of a wavelength to get an impedance here that is very high, and then I put the selective load for the notch frequency to make sure I have 50 ohm impedance here. So the receiver will see 50 ohms into this hybrid splitter. Now, this makes a significant difference. The noise dBc per hertz that I see stays at about minus 184, 185 for attenuator settings, almost all of them. With very high attenuation, there are accuracy problems, but it seems that this is the correct reading for this local oscillator. And I don't see any compression anymore. That was caused by changing impedance. While stepping in attenuation, the impedance goes from nearly 0 when the receiver looks into the notch filter, up to 50 ohms when the attenuation is large. Now it is 50 ohms all the time, and I don't have that effect, and I don't see any attenuation. Sorry, I don't see any compression in the high-level mixers I'm using. Next, I insert the SBL1 back-to-back transformer arrangement and do the measurements again. And of course, the carrier level is lower. I have now 16.8 as maximum, while I had 20 without that back-to-back transformer. So there is a 3.2 dB loss. The noise I see is much higher. It's at minus 181, and it improves at lower signal levels. I don't see compression because the impedance problem has been fixed. I do see some compression in the back-to-back transformer that comes from the carrier that I observe on the spectrum analyzer. It doesn't change with the attenuator setting completely, because it gets a little bit stronger at high attenuator settings. But the compression is small, it's about 0.2 dB at most. But the important lesson is the noise is at high signal level, minus 181 dBc per hertz, while without that back-to-back transformer it's about 3 decibels better. So the reason that the Schottky diode mixers give sideband noise might be entirely caused by the transformer. I don't know this, but I will try to understand and try to make some experiments to clarify the situation. Here is a prototype of a high-level mixer. I'm using much bigger transformers, these ones, and the diodes are ordinary silicon diodes, 1N4148. So here is my new high-level mixer. Each leg has 3 1N4148 diodes in series. And this trimmer and trimmer capacitor, they are to set the isolation between the two RF ports, because that is a good idea to make the injection locking between the two oscillators small.
The new mixer fails badly. The noise floor is unstable and about 10 decibels higher than it was with the other mixer.
I think I found a problem. I have one of the transformers here in contact with one side of the ohm meter. And then I look at the other end of the wires. You see 30 kilo ohms. Another wire here, 28 kilo ohms. And here, well, it's hard to get contact with them. So I have damaged the insulation while winding the transformer, and this is a poor connection, which then probably is noisy. So I make new transformers with wire wrap wire, plastic insulation, which will survive this, putting them on this course, hopefully. The plastic isolation solved the stability problem, but with the 1N4148 diodes, the noise was still about 10 dB above the noise I have seen from the balanced mixer from Mini Circuits, the groups of 4 such mixers. So now I have changed the 1N4148 to some Schottky diodes that I happen to have. Since the forward voltage drop is smaller, I have put 4 of them in each place for the diodes. But still, the noise is not better. The 2 mixers I have differ by about 3 decibels, and this is about 2 decibels worse than the worst of them. So I don't know how it happens, but the noise I see originating in the mixers, this seems to be a natural limit of some kind. I have verified that these transformers, when connected back to back, do not give any sideband noise that I can detect. So the problem must be related to the diodes, I think.
That is consistent with this report from National Institute of Standards. They are measuring phase noise when using mixers as phase detectors. And what they observe at 50 kilohertz is at best maybe minus 184 for one particular mixer, and others are not quite as good as that. So this method using frequency mixers seems to have a limit about at this level.